Great. So Jay Larson. Jay worked at the Argonne National Lab and the University of Chicago and NASA's Goddard Space Flight Center, and is now a fellow in mathematical sciences at ANU. And he's the author of over 70 refereed publications in theoretical physics and plasma physics and climatology and weather forecasting and computer science. And he was the co-lead developer of the model coupling toolkit and an architect on the community climate system model, and a Python wrapper for that PyCCSM. So he has a undergrad and PhD degrees in maths and physics. And he's going to be talking to us today about high-dimensional grid of data. Please welcome Jay.
Thanks. Can everybody hear me? Okay, we're off to a good start. Yes, so as Ed pointed out, I am basically a recovering theoretical physicist, and and as some of my colleagues say, have I tried to make amends for my theoretical physics? Well, no, that's why I'm still in recovery. Anyway, so I'm going to spend some time talking about, well, just a few basic tricks that one can use to play around in high-dimensional space. Now, the problem is probably describing the problem itself is going to take a little bit of time. So we'll try to do that as best as possible without, burning up all the time doing that. So the next 20 minutes will go by quickly, I suspect. So let's go. Okay, so as the title says, lost in high-dimensional space, Python to the rescue. Well, what do I mean by that? Well, I just mean there's a large number of spatial dimensions for a problem, and suppose you want to discretize each of those dimensions, and suppose further, just for the sake of argument, you want to discretize them with the same number of axis points in each dimension. Okay, just work with me on this. Now, should you choose to do that, you'll find the number of grid points in this d-dimensional space will grow exponentially with that dimension. And there is a very glamorous and well-known term for this. It's called the curse of dimensionality. Now, there are attempts to try to tackle this in high-dimensional systems. One of the best tools for it is something called a sparse grid. Now, a sparse grid is a mechanism for providing fine-scale detail in each of the individual dimensions and providing some varying degrees of detail in shared multi-dimensional subspaces, but not the complete story. And these things typically are constructed from a number of coarser grids that are called component grids. And those have fine scales in some dimensions, coarse scales in others. And when you bring all of these things together, you get something that looks like the diagram above in 2 dimensions. And so you'll see that says level 6 sparse grid on closed unit square. Well, what is level 6? Well, again, for the sake of reference here, we're talking about power of 2 partitions of axes. The code I've written does not make these assumptions, but just to kind of give you an idea of how mathematicians usually look at these things and manipulate them and argue about them. Power of 2. So 2 to the 6th is 64. So the full grid in that case would be 65 by 65 because it has the boundaries as well. And what you're seeing there is you can see a dot where each of those sparse grid points shows up. We'll talk about exactly how that's generated in a slide or two. Now, here's something for the cube. That's a level 5 sparse grid on the closed unit cube, so it has the boundaries. And so that means the maximum resolution is 32 well, 33 grid points in any given dimension for the full grid. I would add, these pictures were generated with the code I've written to do these things. So it literally is this stuff, you know, we just did some math. The sizes of the dots correspond to how many of the component grids on which that grid point lives. So you can see some of them are quite small and some of them are quite large. So they're common to many grids if they're large. Okay, so these things are very powerful for reducing. You know, you can get a lot of bang for the buck, so to speak, because you can get a lot of coverage, you can get some fine scale information, you won't get all of it. And asymptotically, the growth rate of the number of grid points looks something like this on a sparse grid. And here is the full grid, which is exponential with the dimensionality. As you can see, this grows a little more weakly. And you can define a complexity ratio as well, the complexity reduction ratio, just by the reduction in the sizes of the sets of grid points. And I think it's, you know, it's pretty dramatic. You may notice here this color bar, it's a common scale. This is log base 10 of those results, because we're talking about going up to 20 dimensions and up to thousands of grid points on each axis. So these things are very useful in a lot of applications. So optimization and density estimation in systems that have large numbers of variables. Solvers, which is more the area where I work, and in particular on trying to use some of the redundancy in this to come up with algorithm-based fault tolerance. And there are all kinds of reasons why you'd want to do that. Are any people in here involved in high-performance computing? Yeah, a few of you. So there are a few people, if I say the word exascale, they know what it means. How about everybody else? Now, it's not like I said skull and bones, or there aren't a bunch of guys who have to leave the room now. Okay. Anyway, on these systems, the large numbers of hardware components can mean that you get lots of failures, you know, happening during runtime, and you need to be able to code your applications to be able to deal with that. And so that's kind of one of the main drivers behind a lot of this work. Now, how do you construct these things? Yes, I know there's a lot of math there. Let's not concentrate on that too deeply. Just suffice to say, there's something you can call the scale lattice that gives you some idea of how finely you're partitioning space on each axis and in multi-dimensional space. So you think of this as just a big grid, and the coordinates of that point are integers, and that on each site, the index for that dimension tells you have, say, 2 to the I or 1 plus 2 to the I points on that axis. And so you can define these collections of component grids on the scale lattice, and then the idea is that you have these things, you can look at redundancy relationships between them, you can come up with combination formulas for, say, suppose you solve a problem on all these different grids, how would you combine them? You know, how would you do a linear superposition of them to calculate on the sparse grid an approximation to the full grid solution? And the level of complexity reduction you get for this is quite dramatic. So even though this sounds a little bit crazy that suddenly you're managing lots of these different grids, you may be doing considerably less work, it may parallelize quite well, and you may get fault tolerance for that. So this is how these kind of things work. You pick a set of coarser component grids. Well, I'll show you a better geometric picture of this in a moment. Solve the problem on each grid, compute a linear combination solution, and perhaps you also have to then do some interpolation if you happen to have the full grid solution as a benchmark against which you can try to ground truth your techniques, and then also propagate the solution back to the component grids if you're trying to do this iteratively. So you can think of these update cycles. And if you have error bounds for your schemes, you can go to town, modeling the errors. Now, what there is here is just a general combination formula with the coefficients. This is something called the classic combination. Don't worry about the exact form of this right now. There will not be a quiz on this. Here is the intuitive picture I promised. So if you look over here, how well does this show if I do that? Oh, that's reasonably well. So this is in scale space in 2 dimensions on the scale lattice. So here, this first cell is essentially 1 grid point in that direction and 1 grid point vertically there. And if you just go outwards, you find, these are kind of higher resolution in X or Y, depending upon where you go. And you may notice this redundancy thing I talked about. If you think about 2 grids here, you're adding them together, there is an overlap between their grid points, and that's what that negative sign is about. So you're trying to correct for some redundancy. And then the beauty of this is that you can get situations in which if you lose a grid, suppose you compute even more solutions on other component grids, you can recover and compute an approximation to the solution. Okay. Whew. Okay, so that's the general game plan as far as math goes. Now, what I've described, obviously there's some complexity to this. There's some high-level complexity. We're talking about, well, I've got to manage all of these things I'm running. And at first, if you go back to this picture, you say, well, what are you talking about, Jay? It's like, come on, you can count them on your fingers and toes. That's not many. Well, if we're talking about higher dimensional systems, very quickly the number of these component grids can grow. I mean, it grows like binomial coefficients, sums of binomial coefficients. So it can grow quickly, but manageably. So if you talk about a 6-dimensional problem, say a plasma physics code, where you're doing things in phase space, you can easily get up into 1,000 or more component grids. So you're talking about something where we might be managing a lot of things that are running. Each one might be parallel. So we're talking about as a high-level complexity thing. There's a lot of stuff to drive and monitor and combine. And that is a reason for using Python at the high level. Now at the low level, we're talking about mesh and grid representation. And the meshes, again, that's tractable for a Cartesian grid. You think, well, I just need all the axis points in each dimension. The way I happen to do this is, it's literally a list of NumPy arrays that do this. That part's easy. Now the gridded field representation in high dimensions, that's more of a problem because, of course, it's growing multiplicatively. So this brings us to one of the central things. I need to start working with arrays in high dimensions. Now, if you look at what other languages support as far as things go, I mean, Python sort of sits in the middle on some kind of logarithmic scale of the number of dimensions it readily supports. I don't know for a fact whether or not you can recompile NumPy successfully to jack up the number of dimensions. I would think almost certainly you can. But more importantly, it's this syntax for dealing with the array elements. And the first tool out of the box people would use for this is virtual linearization, where they just unravel multi-dimensional index space to a single index. And inside of Numpy, that's what's going on. But if you're just walking into this and programming it yourself, you say, do I have to do this in C++ or Fortran and mess around with it? Well, I would hope not. And Numpy offers a lot of advantages. The key one is this thing at the bottom, indexing objects. Have people used these before? Show of hands. A few people? Okay. Yeah, it took me a while to discover this. I'm a little ashamed of how long it took me to discover it, but the idea is that you can use the Python slice intrinsic and create these things and then work with them directly. And so if you look at that first example box there, you can see the syntax for that's quite satisfying. It's easy to build. Okay, I need a tuple of these slices, and off I go. As opposed to brute force, where you pick, oh, how many dimensions is it, and so on. Okay, now, for that classic combination, you may recall there were problems with finding parts of the scale space that meet conditions, that they're in the classic combination. Again, NumPy really can rescue on this because, numpy.where. Basically, it's that simple. Play with things like that. And another problem you run into is finding neighbors. Say you want to construct a finite difference scheme, or you want to do high-dimensional interpolation. Now, if you think about a high-dimensional analog to what is called the 5-point stencil in 2 dimensions, which is, north, south, east, west. Again, it's rather easy. You can just use the NumPy identity matrix and just pull rows off of it and kind of go plus or minus off of things to figure out how to index these things and find neighbors. Now, as far as something more complex, if you talk about the compact stencil, you need to look at using some toys like iter tools, but literally, I mean, this little block of code here, you can go do this in the number of dimensions supported, and there you go. And I think we're really near the end, and I've kind of revealed just a few tricks, and I don't know if these are new to many people or not. They were new to me when I ran across them, and I was quite happy to find them and quite relieved. So this is all being incorporated in something called the Python Grids and Fields Toolkit, whose development, well, I'm the main guy writing the code day to day, and I have some help from people, well, one guy at Fujitsu and a student at the ANU named Brendan Harding. And at this point, we're looking at releasing an early version of this late this year. And this is part of an even bigger agenda of building a numerical analysis friendly MapReduce framework. MapReduce, most people know MapReduce is brilliant when you don't know structure a priori, right? Because you just turn it into keys and values, and if you've got a big global sort that's fast as blazes, it comes right out. Well, a lot of this kind of functional programming is very attractive for doing this stuff, but we know the structure a priori, so it's really about building something that will do that. And that's pretty much the story. All of this is under construction. I hope to have a lot of it released in the new year. And thank you for your time.
Thank you very much.
Thanks.